Hi there, and welcome to tutorial 7 on inverse functions as they arise on the Edexcel Core 3 Maths A-Level syllabus. As always, we take a look at what Edexcel says we need to know. We've previously defined a function and the domain and range of a function, the domain being the input numbers, the range being the output numbers. We've talked about composite functions where two or more functions are combined, and we have talked about terminology. In this section we're going to do inverse functions and we're going to talk about their graphs, and Edexcel says students should know that if f to the minus 1 exists, i.e. if a function has an inverse, then f to the minus 1 of f of x equals f of f to the minus 1 of x is equal to x. We're going to talk about that. First things first, what are inverse functions? Well, an inverse function is related to the original function f, and it maps back from the range of f to the original domain. We write the inverse function as f to the minus 1. Now, let's just think about this a bit more clearly. You take a number, for example 2 here. You apply a function to it, the double function plus 1. You double it and add 1, and you get 5. Your function f brings you from 2 to 5. The inverse function brings you from 5 back to 2. It is a function that will undo what f did. So for any number you put in, f brings you to the range of f. Okay? And then this inverse function, if it exists, would bring you back from what was the range of f to the original domain of f. It would bring you backwards. Now in this simple case, you double add 1 to go backwards from an original number that you put into the inverse. You must subtract 1 and half. That is the opposite of doubling then adding 1, is subtracting 1 and then halving. Now, f is a function, and the inverse, f of f to the minus 1 is a function. And they both have a domain and range. Now, the domain of the inverse function, okay, the numbers you put into the inverse function happen to be what the range was of f, and the numbers you get out of the inverse function, the range of f to the minus 1, well, they are the original numbers you put into f, the domain of f. And it's very important that we realize this, that the range of the original function is actually equal to the domain of the inverse function, and the range of the inverse function here, the numbers you get out having applied the inverse, is actually the domain of the original function. And this is a really important idea that I'll stress throughout the video. In a lot of exam questions they give you a function and they ask you to state its domain and range, and then they ask you what the inverse function is and they say hence state its domain and range. Well, the inverse function, its domain would have been what the range was of the original function, and its range is what the domain was of the original function. So you don't have to go about by drawing and reworking out. You can just use this very important rule here. Okay, just want to also clarify a bit of notation they said we must know in the examination scheme of work or syllabus. If you have an original function f of x, then its inverse is f to the minus 1 of x. You need to be familiar with that type of notation. And something more important, a bigger principle, just to fully understand what's going on with functions, we need to understand this line here. Now, the way I'm going to do it is as follows. I'm going to use a red here in order to show this. So imagine you take an input number x. You apply f to it. So over here you get f of x. Then you applied f to the minus 1 to it. So along here you applied f to the minus 1 to f of x, going backwards. What would you get? Well, you'd get your original number back, x. So x, you apply f of x to it, and the whole point of an inverse is it brings you back to your original number. Hence, f of x done first and then f to the minus 1 applied to it gives you your original number back. And hence f to the minus 1 of f of x equals x. I'm going to show it the other way around. This time I'm going to start over here with a different coloured pen. I'm going to start here and say, imagine you take a number here and you apply the inverse function to it. So you have f to the minus 1 of x. And then you apply f to it. So you have f of f to the minus 1 of x. What do you get back? Well, you get back what you started with. That's the whole point of inverses. Hence, if at first you do f to the minus 1 on x, and then you do f on that, you get your original number back. So this is just something you should be familiar with. If you apply a function to its inverse, you get the original number back. If you apply the inverse to the original function, you get the original number back. Okay, now we're going to talk about when you can have inverse functions. Imagine you had a one-to-one mapping. Here is a one-to-one mapping. Each element on this side maps to a unique element on that side. If you could find a mapping that gets you from there to there, and that happens to be a function because it's one-to-one, could you go backwards? Could you find a function back where you can find a mapping back, the opposite mapping, and it is a function because it is also one-to-one? Everything here would get mapped by the opposite function to a unique element in the original domain, and that's fine. Now imagine you had a different function which was going this way, many to one. So for example here, two different inputs give you the same output. Could you find a function back? Well, you could find a mapping back that brings you back. It would be the opposite of this function here. However, it wouldn't be a function because one input gives you two different outputs, okay, and that would be a one-to-many mapping, and we know that one-to-many cannot be a function. So you couldn't find a function backwards. So hence there is no inverse function. Okay, there may be an inverse mapping, but it's not an inverse function. So a key idea here is that an inverse function only exists if the original mapping is one-to-one. And that's something that we're going to need to bear in mind. If a function is maybe many to one, we might have to restrict it in order that it has an inverse over a certain portion, but as an entirety it would not have an inverse function, and that's something we have to keep in our heads. Now let's think about finding inverse functions. Imagine your original function is 3x plus 4. You take a number, you times it by 3, and you get 4. What's the inverse? Let's first of all just talk about what the domain and range are. You can put any number in here as the domain, and the range, what do you get out? Well, you also get any number out, and I'm going to just say f of x is any number, okay? Because obviously you know it's a straight line graph like that. So what's the inverse function? Well, what's the opposite to timesing by 3 and adding 4? The inverse function, the opposite to timesing 3 and adding 4 is subtracting 4 and dividing by 3. Now, we could think of what the domain and range of the inverse function are. However, we know the domain of the inverse function is the range of the original, so we know that the domain must be all real numbers, and we know the range, well, the range is the domain of the original function. So again, the range of this function, f to the minus 1 of x, must be all real numbers. And we could draw these. It's always helpful to draw these. So if we drew the original function here, f of x, it would look something like that, and the inverse function would look something like that. Maybe if you could just pause for a second and have a look at those graphs and see if you can see how they are related to each other in any way. I'll come back and I'll talk about the relationship afterwards, but just see if you can spot it for yourself. Another one here, we've got a function, g of x is 5x minus 2. What x numbers are in the domain? What can you put into that function? Well, you can put anything. X is a member of the real numbers. What's the range? What do you get out when you put any number in? Well, you get all the real numbers out. Remember, it's a straight line graph, looks something like that. So you get all the numbers out. What's the opposite of this? What's the inverse function to multiplying by 5 and then subtracting 2? Well, it would be to take a number, to add 2 to it, and then divide by 5. What's the domain and what's the range of this inverse function? Well, the domain of the inverse is the range of the original function, so the domain must be all real numbers as well, and the range of the inverse function is the domain of the original, so g to the minus 1 of x must be able to take all real values. And if we drew the graphs of both of these again, the first graph here would be g of x, and here would be g to the minus 1 of x, and I encourage you just for a second to see if you can spot how those graphs are related to each other. Again, I'll come back and mention this towards the end. Let's have a go at another one here. Here's a function, and it's the squared function. You take a number and you square it. Now, what is the domain? What numbers can you put in here? Well, you can put any real number in there. So the domain is any real number. What's the range of that? Well, you know that the square function looks something as follows. Okay, so it looks like a parabola, a U-shaped parabola, and the range is f of x has to be bigger than or equal to 0. Now we've got a slight problem here, and we've got to be very, very careful. Currently, this function is a many-to-one function. Okay, many x's, like for example -2 and 2, give the same y output, and we know that a function only has an inverse if it's 1-to-1. So if we wanted to make it have an inverse, we'd have to be very careful and maybe restrict it over a certain portion so that a portion of it was 1-to-1. So we couldn't take the domain as follows. We would have to restrict the domain and say, for example, maybe x is bigger than or equal to 0 is our domain. Now, what's the opposite of squaring? Well, the opposite of squaring is to take a number and to take the square root of the number. So that would be the inverse function. And what is its domain and its range? Well, its domain is the range of the original function, so x has to be bigger than or equal to 0, and the range, well, the range is the domain of the original function, so f to the minus 1 of x has to be bigger than or equal to 0 here. And let's just draw these. Let's draw x squared, the restricted x squared, and draw the square root function. That's originally x squared, but as I said before, I have to restrict it so x is bigger than or equal to 0, and this is my f of x, and this is my f to the minus 1 of x. And you see here x has to be bigger than or equal to 0, and the range is always bigger than or equal to 0 as well. Again, look at those graphs and see if you can spot how they are related, and I will come back. And let's have a look at another one. G of x is x squared plus 2. Now, let's think of what the domain is for this. Now, if you just drew the graph as it is, it would look something as follows. It would cross at 0, 2. Again, that's a many-to-one function, and we can't have an inverse of a many-to-one function, so you could restrict it over a certain domain so it was 1-to-1, maybe x bigger than or equal to 0. So we'd have to restrict this so it was invertible to be x bigger than or equal to 0. In that case, what would the range be? Well, the range would be all the values bigger than or equal to 2. The function can take all the values bigger than or equal to 2, so g of x would be bigger than or equal to 2. Okay, let's think about what the inverse is. The inverse, what's the opposite to squaring and adding 2? Well, the inverse function would be take a number, subtract 2, and take the square root of it. What would its domain be? Will it be the range of the original function? So x would have to be bigger than or equal to 2 for it to make sense. And the range, well, the range would be the domain of the original function, and it would be g to the minus 1 of x is bigger than or equal to 0. What would the graphs look like? Well, here's the original x squared plus 2 graph, but I need restricting it. So I restrict it so x is bigger than or equal to 0, and here would be my inverse function. So this is my original g of x, and here's g to the minus 1 of x. Again, take a look at those and just see if you can spot the relationship between them. We have another example here, example 5. We have a function which is you add 2 and then you square. What is the domain of the original function? Well, let's just think what this graph looks like. X squared looks as so. X plus 2 squared is a shift 2 units towards the left direction here. Now, I'll just redrew that out as a shift. If that was that, there would be the point minus 2, 0. Now, if we want to restrict it so it's 1 to 1, we'd probably have to restrict it there and ignore that side. Or we could do the other way around, but usually we go this way around. So the domain here would have to be x is bigger than or equal to minus 2 for it to be 1 to 1. And the range, well, x can take any number bigger than or equal to 0. H of x can take any number bigger than or equal to 0. What's the opposite function? What's the inverse function? Add 2 and square. Going backwards, you would take a number, square root, and then subtract 2 off that. Now, we need to think what the domain is of this. Well, the domain of this function must be the range of the original, so it's going to be x is bigger than or equal to 0, and the range is going to be the domain of the original, which is h to the minus 1 of x. It's got to be bigger than or equal to minus 2. And again, let's just have a look at these graphs here. As I said before, we have to restrict that function, so the domain of that function, so x is bigger than or equal to minus 2, and we would so get the following original function restricted and the inverse function h to the minus 1 as such. Okay, now just as we look through here, hopefully you spotted this as we go through, but I'm just going to point this out now and come back to it later. These graphs, the original function and the inverse, are always a reflection of each other in the line y equals x. I'm going to talk about this in a second and why, but again, that's a reflection in the line y equals x. Example 3, reflection in the line y equals x when that's restricted. Reflection in the line y equals x, and going back to the last one, a reflection in the line y equals x. So the original function and the inverse function are reflections of each other in the line y equals x. Okay, your turn now. I would like you to find the inverse of each of the following 5 functions, and I would like you to state its domain and range. In 10 seconds I will go through. Pause the video now, have a go at these. Okay, let's go through these then. First things first is whenever I deal with the original function, I take note of its domain and I also think about what its range would be. The range here, f of x, I know that's a straight line graph, so f of x could take any real number. Okay, so in a different coloured pen maybe, what's the opposite function, what's the inverse function of doubling the original number and adding 3? Well, you take the original number, you subtract 3 and you halve it. And what is the domain of this original function? Well, the domain is equal to the range of the, what's the domain of this inverse function? It's equal to the range of the original, so x is a member of the real number, real numbers, and what's the range of the inverse function? Well, it's equal to the domain of the original function. So again, it's as follows. Okay, here, f of x is equal to 1 over x. The domain is the real numbers apart from 0. Okay, what do you get as your range here? Let's just think about the range, always helpful. The range is any real number, but again, you don't get 0. So excluding 0, I'm just going to say excluding the number 0 there. Okay, what is the inverse of doing 1 over a number? So if you do 1 over a number, how do you get back to the number? Well, it's 1 over again. Okay, the opposite to inverting a number would be to invert it back. So the inverse function is actually equal to the original function. And what numbers can you put in? Well, you can put in the real numbers excluding 0, x, I'm going to say x not equal to 0, because the domain is equal to the range of the original function, and because the range of the inverse function is equal to the domain of the original. So again, the domain of the inverse function is the real numbers but not equal to 0. Okay, let's do the next one. Here we've got a function. You take a number and you half it, and you can get any number out of that. So you can put any number into that. So the range is any real number. If you drew that as a straight line graph, it would be any real number as an output. What's the opposite to halving a number? Well, the opposite to halving a number is to double a number. And because the domain and the range were both all the real numbers, in this case, the domain and the range will also be all the real numbers. Okay, slightly more tricky here. Your original function is 4 subtract x, and x can be any number. Now that's a straight line graph. We know that's a straight line graph looks something as follows. So we know that the original function can take all values, can take any value. So its range, f of x, is any real number. But I suppose what's the inverse? Well, instead of 4 subtract x, you can think of it as multiplying by -1 and then adding 4. Multiplying by -1 and then adding 4. So what's the inverse? Well, you take a number, and so you multiply by -1 and then add 4, so you subtract 4, and the opposite of multiplying by -1 might be dividing by -1. Okay, dividing by -1 is the same as multiplying by -1 effectively, so this would be 4 minus x as well. So again, the original function and the inverse function are the same as each other. Both the original function had domain and range all real numbers, so the inverse function has domain and range all real numbers. And lastly, you've got the cubic function, where the domain is all real numbers. The cubic function looks as so. So we know that its range can take any real number, any y number can be taken there. So what's the opposite of cubing a number? Well, it's taking the cube root of a number. And its domain and range were all the real numbers, so the inverse function will have domain and range all the real numbers as well. Okay? Okay, and now something we've talked about previously. How do we draw the inverse functions? Well, we've already mentioned that if we have an original function f of x, the inverse function f to the -1 of x is the reflection of the original function in the line y equals x. And that's something you need to be aware of and need to be able to perform by drawing original functions and inverse functions, etc. A little bit of intuition of why that is. Well, let's just say we've got an original function and we put an x number in. Okay, we put an x number in and we get a y number out. So these coordinates here would be, you put x in, you get f of x, which we're going to call, say, y, a number y, out. Now, if you reflect something in the line y equals x, what it does to any particular coordinate is it flips the roles of y and x. So a coordinate, say for example 1, 2, after you've reflected it in the line y equals x, would then become the coordinate 2, 1. The coordinate, say 3, 8, after reflection in the line y equals x, would become 8, 3. Okay, so if you take xy and you reflect it in the line y equals x, you would get yx. So if we take all the points on the original curve and reflect them in the line y equals x, effectively what it does is it flips the roles of y and x. So say for example over here, if you did put your y number in that you got out of here, say this number here was at your y, if you put that into the inverse function, out the end of it would come x. So the inverse is the reflection in the line y equals x because it's flipping the roles of x and y. It allows you to put y into the function and come back out with x because of that very flip. So there's some intuition of why inverse functions are reflections of each other in the line y equals x. The thing we need to do here, we need to look at how to find the inverse functions of more complicated original functions. And I'm going to talk through what these boxes mean here. These are the ideas behind it. But here, imagine we have a function, f of x is 1 over x minus 3. It's harder to think what happened to x and to take that process backwards. So there's a more formulaic method I'm going to show you now on how to find the inverse function. And the idea is as follows. Just before we go into that idea, in fact, let's just state, as we always should, what the domain and range of this function is. Here, x can take any real number apart from x should not equal 3 because then it would make the denominator 0 and you can't divide by 0. What is the range? Well, you know 1 over x graphs look something like that, and 1 over x minus 3 is a shift 3 units to the right, so it would look something like this here. So what's the range? Well, the range is any real number apart from 0. So f of x can be anything, but f of x cannot equal 0. Okay, now here is the basic idea of this. We put an x number into this function, and let's just call the output number we get when we put x in y. So y is equal to x subtract 3. Now what this is telling us is we put an x in, we get a y out. If we could rearrange this equation so x was the subject of the formula in terms of y's, then that would be a function effectively that puts y in and gets x back out, which would be the inverse. So if we rearrange this, okay, and we want to make x the subject, then we would have a function that brings us from y back to x. So we would multiply both sides by x minus 3 in this case to do this. So we would have yx minus 3 is equal to 1. We would multiply out the brackets to get yx minus 3y is equal to 1. We would add 3y to both sides to get yx equals 1 plus 3y. And we would divide both sides by y, assuming y can't be 0, and we would get x is equal to 1 plus 3y over y. And that now is our inverse function. It is a function that puts y's in, the y's we got out from the original function, and gives us back the x we had put into the original function. We don't leave functions in terms of y, so at the end we would state that f to the minus 1 of x is 1 plus 3x over x. Okay, and these are what these boxes were saying. The basic idea was to determine the function that gets me back from the y value to the x value by making x the subject of the formula, and this is then your inverse function. Step by step what we did to find the inverse function f to the minus 1 of x, put the function equal to y, rearrange to give x as the subject of the formula, and then rewrite with f to the minus 1 of x and replace y with x. We should say what the domain and range are. The domain of this function must be the range of the original function, so x cannot be equal to 0, but it can be any other real number. That's the domain. And the range in this case would be the domain of the original function, so that would be f to the minus 1 of x cannot equal 3. And that's how you do that. So I'd like you to have a go at one very similar to this yourself. Pause the video, have a go through, state the domain and range of the original function and the new function, and see if you get the inverse function correct. Pause the video and I'll go through in 10 seconds. Okay, stating the original domain and range. The domain here is all real numbers apart from x can't be 1, and we know that say 3 over x looks something like that, and 3 over x minus 1 is a shift 1 unit to the right, so it would look something like that there. So our range, f of x, can take any value, but it cannot take 0 is our only restriction. How do we find the inverse? Well, we put x into the function and we get a number out which we're going to call y. We're going to rearrange this to make x the subject of the formula in terms of y's, so we have a way of getting from y's back to x. So we multiply both sides by x minus 1. We get x minus 1 multiplied by y is equal to 3. So we get xy minus y is equal to 3. We add y to both sides and we get xy is equal to 3 plus y, and then we divide both sides by y and we get x is equal to 3 plus y over y. And we rewrite as f to the minus 1 of x is equal to 3 plus x over x, and our domain is the range of the original function, so x cannot equal 0, and the range is the domain of the original function, f to the minus 1 of x cannot equal 1. And we're done, and that's it. We found the inverse. Something worth pointing out here is sometimes functions are equal to their inverse. Okay, so when a function is equal to its inverse, it's called it's said to be self-inverse. That's to say that if you find the inverse and it's the same as the original function, then you have a self-inverse function. Here's an example. Show that the following function is self-inverse. Well, if we could find the inverse and it was equal to that, we'd know it was self-inverse. So, to find the inverse, we let y equal to x over x minus 1. We then make x the subject of the formula, so we multiply by x minus 1. We expand the bracket. We add y to both sides. Sorry, at this stage we're trying to collect all the x's together, so what we would do is we would subtract x from both sides and we would add y to both sides, so that would give us yx minus x is equal to y. Then we would factorize, so we get x, y minus 1 equals y, and x is equal to y over y minus 1. Finally, we would just write that in proper f to the minus 1x notation, and that would be x over x minus 1, and we have shown that the inverse function is the same as the original function, and so it is self-inverse. Important point obviously to mention here, define this, the domain here, x cannot be, is a member of the real numbers, but x cannot equal 1. Right, have a go there. See which of those are self-inverse functions. See if you can find which ones are invertible. Pause the video, have a self-invertible. Pause the video, have a go, and then I'll go through the answers in 1 second. We knew the inverse of this. The inverse of this is an easy one. Double and add 3. The inverse is simply subtract 3 and half. That is not self-inverse, so no. What is the opposite of taking the reciprocal? Well, it would be taking the reciprocal again. So f to the minus 1 of x here is 1 over x, and it is self-inverse. What's the opposite of dividing by 2? Well, the opposite of dividing by 2 is doubling, so that is not a self-inverse. Here, this is maybe slightly more complicated to think about, although we did it earlier. Let y equals 4 minus x and make x be the subject of the formula, so x would be 4 minus y, so f to the minus 1 of x is 4 minus x. It is indeed a self-inverse, and what's the opposite or the inverse of taking a cube? Well, it's taking the cube root, and that certainly is not a self-inverse. Okay, so this one here and this one here were the self-inverses there. A bit of notation warning and then we're finished. A couple of things to say. Imagine your original function was, say, double the input, so y equals 2x, or f of x is 2x. If I said to you f of x all raised to the power of minus 1, I'm taking the reciprocal. I am taking the reciprocal of f of x, so I'm working out 1 over f of x, which is 1 over 2x in this case. However, the notation we've been using so far is f to the minus 1 of x, and that is the inverse function. The inverse function of doubling is dividing by 2 or halving. So it's very important to note that f to the minus 1x means the inverse function of f of x, not the reciprocal, which we would denote f of x all to the power of minus 1. And that is that for now. I would advise you to read chapter 2, page 23 to 27 and work through the examples. Then do exercise 2E, questions 3 to 8. Then mix exercise 2F, every single question. And then I would be confident that you would know everything there is to know about functions for Core 3 Edexcel. Thank you for watching. I hope you found the following video useful.